we move on to the second advancement, right. Second advancement is bit more complex than pulse GMAW, right. So, when you are doing a short circuiting transfer, the issue is here is to achieve a stable transfer, right. So, when you are doing a short circuiting, like in a last lectures when I was talking about metal transfer, the moment you have a short circuiting happens, the voltage becomes very low, almost 0, is not it, because it is continuous, the circuit is completed. So, voltage decreases significantly the moment short circuiting happens, but the current is still flowing the same amount what you are transferring. So, that means that when you are forming a droplet, when the current is there continuously flowing, so you also create an enormous amount of Lorentz force and magnetic force, which is constricted to a very tiny area. It gets accumulated because of the resistance of the liquid, it is much lower. So, it is getting accumulated in the droplet. So, moment the current is Lorentz force accumulates, so obviously it would explode the droplet, is not it, right, because you have a bridge formed between a two solid and liquid bridge is forming, which has an extremely poor electrical conductivity. Okay. So, the accumulation of charge carriers at the droplet would lead to a generation of enormous amount of Lorentz force and magnetic fields, right. And then obviously moment you have a short circuiting happens, and the accumulation of force will lead to the explosion of the droplet, and then that can lead to severe turbulence in the whirlpool. Obviously you will throw whatever you melt to various places, and that causes a spatter, is not it. So, now we will have to identify some mechanism so that we avoid such an unstable process and metal transfer characteristics. So, there are various ways people have attempted this. So, one such mechanism is to identify the moment at which short circuiting happens. Okay. The moment we identify that moment, we can reduce the current, okay, in such a way that the current is minimized to so low and the droplet can be transferred intact just by surface tension. Okay. So, you have a droplet is going down. So, the moment short circuiting happens, you identify the voltage drop. You know that when the short circuiting happens, the voltage becomes very low, 0, and then immediately you reduce the current, okay. And then everything, the system, the current is low, the voltage is close to 0, and it is just a droplet, okay. Suppose if you pull the droplet back, the surface tension of the whirlpool would pull the droplet, is not it. So, by doing so we can achieve a very stable transfer, but then the trick is we have to identify at what moment the short circuiting happens, so that we can turn the current off, right, it is clear. So, that is how the modern advancement took place in GMAW by modifying the current voltage waveforms. So, one such waveform is given over here in this slide, which is commonly used to achieve a short circuiting transfer, okay, at extremely low droplet temperature. Low droplet temperature means close to melting point, okay. That is what is known as, this process known as cold metal transfer. Okay. So, first I will show you the video, then I explain this waveform, and then again we will look at the video to understand, is not it. Okay. So, first we will see the video, how does the process work. So, you see the various processes what is that are happening. So, you see that the wire is moving back and front, is not it, and we have a short circuiting event, and we have arcing event and the short circuiting event, and the arc completely extinguishes and the droplet is transferred, and then again the wire is moving out, and then arc is formed again, and then the cycle continuously carried out, and the droplet is transferred, and you see the molten pool, is not it. So, in order to achieve this, we need extreme synchronization. So, we will have to control the wire feed rate, we will have to control the arcing period, we will have to control the moment at which the short circuiting happens, and then we will have to measure the moment at which it happens, and then we will play around the waveforms in such a way that the droplet is transferred without any explosion, right. So, it is clear, right, the actions, we have arc, we have the back and front movement of the electrode, the short circuiting event, and then the metal transfer by the collapse of the droplet to the well pool. So, what it is happening here is, the objective is we will have to transfer the droplet without explosion. That means that the moment short circuiting happens, we will have to minimize the current, okay. But we cannot completely minimize the current, because then when you retract it, okay, so maybe surface tension is not sufficient, so the droplet may come with the wire, isn't it. So, now what we do, so the first we have the arc. In this video we saw the arc is formed. The arc, the moment arc is there, obviously you melt, you form the droplet, okay, and then the wire is brought down towards the pole, okay. The moment you establish a short circuiting by the forward motion of the wire, okay, the current is decreased, and then the moment the wire is completely made in contact with the well pool, the current is decreased, okay. That means that arc completely extinguishes, isn't it. So, this continues from here. So, until this point arc is there, isn't it, and during this process the wire is also brought down. The moment the short circuiting is happening, okay, the arc current decreases in such a way that arc completely extinguishes, isn't it, and during this process short circuiting event, the current is also decreased completely, right. And then now in this position the electrode tip is completely touching the well pool, and then we retreat the wire, okay, we retreat the wire, and during this process we slightly increase the current in such a way that we form a Lorentz force, and the neck would make a pinch at the droplet, and then when you are retracting further, this droplet would be transferred completely to the well pool. It is clear, yes or no. So, the trick is here is we maintain arc current, the arc is there, and during this process the wire is also coming down, and gradually we decrease the current when you are moving it up, and arc is still there, okay. And the moment short circuiting happens, we identify that from the voltage drop, and then we decrease the current to extremely low level to keep the droplet stable, and then the wire is retracted, right, and during this retraction period we increase the current slightly higher, so that the Lorentz force and the surface tension of the droplet would do the transfer from the tip to the well pool. It is clear, and then the cycle continues. The current is extremely low, below even arcing current, because arc is completely gone, isn't it. So, arc is there until only this, and the droplet is transferred, the voltage is 0 and the current is very minimal, because we are just switching off the current when the short circuiting happens. So, that when the droplet is transferred, we are transferring it technically a molten droplet, isn't it. So, by doing so, the arc energy we supply is extremely minimized to much lower level than even in pulsing GMAW. So, technically droplet is transferred at the melting point of the droplet. So, that means that the droplet is transferred in much more colder stage than in any other GMAW process. That is why this process is also known as cold metal transfer. Okay. So, the metal is transferred and the droplet temperature is more or less the melting point of the droplet. So, this has a very high advantages in terms of heat input we give. Okay. So, if you take an average of the I mean of this circuit, it will be much lower than your pulse GMAW, your I mean. Okay. And as well as the droplet is transferred without any arc. So, you are not superheating the melt pool, and you are also not superheating your heat affected zone. So, you can avoid various metallurgical reactions that are happening due to the superheating. For example, if you want to avoid intermetallic formation, right, when you are welding a dissimilar weld. Okay. So, in that case, so what you have to do is we will have to minimize the heat, and then we will have to make sure that the weld pool temperature is not heated up, otherwise you will have a diffusion of alloying elements, which may cause the intermetallic formation. For example, if you are doing iron aluminum weld. So, in those kind of applications, this process is extremely suitable because the heat is there in the weld pool is so minimized such a way that we avoid all these detrimental metallurgical reactions. Okay. And you can also achieve a similar productivity because the cycle is same as like in the pulsed GMAW. So, we make sure that every pulse, every short circuiting, one droplet is transferred, and we can play around with the retraction and the forward motion of the electrode, and the short circuiting event would determine the number of droplets transferred per cycle. Yes, it is clear. Now, this is what happens in the video. We will see a video again. So, first, so this is the time at which the current is slightly increased after short circuiting. Okay. You see that when the current is increased, you form the neck, isn't it? So, I will just use this pen here. So, you form a neck, and then this neck, so it is now retracted, the wire is going up. Okay. Yeah, so now the droplet is detached, isn't it? And then subsequently, so I need 2 more, and then wire is going up now, and then current is increased such a way that you form an arc, isn't it? And then arc stage remains, and upon keeping for some time, and then the wire is again going down, isn't it? So, again the wire is going down, short circuiting happens, voltage current is now minimized to extremely low level, and then droplet is transferred when the wire is coming out due to the surface tension of the weld pool, and then slightly increased current, which can also aid the droplet transfer, right. Now, the cycle continues. So, number of droplet transferred is a function of number of short circuiting events. So, we can have a cycling of the process, right. The process is clear for you. So, the step is the arcing period, short circuiting period, and then the transfer period, subsequently the retraction period. Okay. During arcing period, the current is maximum. During short circuiting event, current is 0, and during retraction transfer period, current is slightly higher, and subsequently we go back to the arcing period, right. So, this is known as controlled dip short circuiting transfer characteristics. Okay. So, now yeah, so there are 2 or 3 companies, they sell the power source with the capability of transferring in controlled short circuiting dip transfer. As we will move on to the last slide in GMAW, this unit is how do you achieve all these developments what you have done GMAW. So, we will have to have a smart power source, isn't it, because the moment you say I want a pulse transfer, then the power source would all calculate the wire feed rate, it has to calculate melting rate, it has to calculate the frequencies, it has to get the process windows of transfer, right. Similarly, when you want to transfer a control short circuiting transfer, and it has to calculate the speed at which it has to move the wire and take the wire back, the forward moment retraction. Okay. It has to calculate the short circuiting time, right, and it has to calculate the current at which it has to form the arc. So, all the information it should be calculated, and then when you select a welding process, and it has to as simple as possible. Okay. So, the famous Einstein's quote. Okay. So, everything should be made simpler, okay, but with complicated means, isn't it? Because when you look at the actual welding process, the welding engineers or welding technicians, they are all simple persons, and you can't tell them to know, okay, so you make the current 0 when the short circuiting happens, and you will increase the current and the moment the wire goes up. No one would buy that power source, isn't it? So, it has to be inclusive, and it has to be as simple as possible. Okay. All the signs what we see here, it should be implicit in the power source itself, and it should be controlled with a single knob or so, isn't it? So, that is how we developed the synergy technology. Okay. So, synergy technology, it talks about synergizing between all the parameters which control the welding performance. For example, we looked at wire feed rate, which is important because you have to maintain a constant arc length, right, in some cases, or you also need to calculate a short circuiting time. So, how do you calculate short circuiting time? You have to know the melting rate and then arc length. Okay. So, if you know arc length and melting rate, then you know at what time short circuiting can establish, isn't it? Suppose if you have a 70 mm per second, that is your melting rate, the arc length is 70 mm. Okay. So, what time after arc ignition short circuiting can happen? Isn't it? So, for example, so you have 70 mm per second, that is the wire feed rate, okay, and then your arc length is 70 mm. If your wire feed is 70 mm, you will always maintain a 70 mm of arc length, isn't it? Suppose if you increase the wire feed to 80 mm, then what will happen? And you are moving your wire towards a whirlpool, isn't it? So, now we can calculate from the melting rate. So, what will be my wire feed rate in such a way that I would establish the short circuiting after time t, isn't it? Because you will have to feed more than your melting rate, and if you know the wire the arc length, then we can see at what time t short circuiting can be established, right? It is clear. But then we need all the information, isn't it? So, the system should contain the information about the melting rate. The melting rate can be calculated based on the compositions, stick out length, and stick out length has to be maintained by the power source. So, the wire feed system should talk to the power source in such a way that in a pulsing case it always supplies the whatever it can melt, isn't it? So, that you maintain a constant arc length and you supply the same melting rate as the wire feed rate, right. In a short circuiting transfer mode, you will have to make sure that you will have to establish a short circuiting after time t. So, then it has to feed up, increase the wire feed rate compared to melting rate. So, power source should talk to wire feed rate, no, I am melting 70 mm per second, you give me 80 mm per second, so that I can establish a short circuiting after so whatever time, right. And then the moment short circuiting happens, and the power source would identify, okay, my voltage is going down, okay, voltage is 0. So, now I need to reduce the current, isn't it? And then it can reduce the current with a delay, with a slight delay, and then you tell the wire feed rate again, saying that you pull the wire back, isn't it? And then the wire feed rate will pull the wire back, and then by the time it goes, it has to measure how much it has travelled, so that the moment it achieves a certain arc length, you ignite the arc by giving the arc current, right. So, these are all now integrated. So, in synergy mode, so what you do is you select a database for a given material and the filler diameter. These two are information we need to calculate the melting rate, isn't it? Melting rate is alpha I plus beta L I square by pi r square. Alpha beta is can be determined from the composition and the welding parameters like shielding gas and the electrode polarity, isn't it? If you know that, we can calculate alpha and beta, because that is all V column I, V I anode current, and these are all process specific, and wire diameter will determine the pi r square, okay, and the L is determined by the power source itself, what stick out length it has to maintain. So, what you will have to choose now to achieve a pulse or any other waveforms, you will have to give what I mean you want and what wire feed rate you want, that is it. These two parameters if you give, the power source would calculate everything. Suppose if you want to do pulse GMAW, so it has to from I mean you can calculate IP and TP, isn't it? From I mean can calculate the melting rate, and the melting rate can be calculated, F can be identified, the frequency of pulsing, and accordingly the melting rate can be calculated from IM, and it can maintain constant arc length pulsing. So, only two information you will have to give, right, information about current, mean current, information about wire feed rate. If you do these two, the synergy control the power source would take care of the entire welding process, because all the database is established from the physics what I explained, from the melting rate calculations, from the heat transfer from the arc to the electrode tip.